Okay, so we've been exploring electric fields, and now we want to write the electric field in the xy plane for a particle of charge, say q star, which has that expression. And we need to turn that into an expression that has x and y coordinates. So let's say we have a y-axis here, and we have an x-axis here. X and y, and we have a particle of charge q star here, and let's just use x naught as its x coordinate and y naught as its y coordinates. Now these are positive numbers because we are in the first quadrant, and we want to find the electric field everywhere in the xy plane, but we can just choose any arbitrary point to develop this general expression. So if I take this and put it anywhere else, we can do the same exact analysis. So we need the distance from here to there to get the r squared in terms of x and y. Well, that's going to depend on this distance and this distance, right? The horizontal distance squared plus the vertical distance squared gives us this side squared, the hypotenuse squared. So what is this distance? Well, it depends on the coordinate x. So this has some x value, which in this case is greater than x naught. So here we have x minus x naught. That's some positive value. And when we square that, we're going to add that to this side, where this corresponds to some y value. So we can leave that as x and y sort of unspecified so that this expression is general. And so now we know how to get the hypotenuse. And so this becomes k q star divided by x minus x naught squared plus y minus y naught squared. And now we've turned the r squared part into a general expression in terms of x and y. Now I just want to point out that this is true, as I said before, for any location. So if we choose a location over here, well, let's maybe do this in a different color. So let's use blue. So let's say we choose a location here. So now the distance is here. That's the distance. Well, it's the same analysis. Here's the horizontal part, and here's the vertical part of this. Well, what's the horizontal part? Well, it's some negative x value corresponding to this, right? So, but we still have to take the difference. It's still x value minus x naught, so we still have x minus x naught here, right? But that's going to be some negative value. And this side is still y minus y naught. Put numbers in and satisfy yourself that that's still the case regardless of where that point is. Right? I can move this point anywhere and do this analysis. I'll always get that the r squared is whatever x value I choose minus x naught for the horizontal part, and whatever y value you choose minus y naught for the vertical part. And so this is a completely general expression. Now we need the unit vector. Well, how do I get that? Well, if I'm just looking at this, then let's make a little unit vector, which would have to be pointing that way. So the electric field points that way. And we need to construct this object. Well, it's pointing that way because it has components, x minus x naught and y minus y naught. But we have to construct a vector. So let's do that in red. So this here is actually a vector, but it's not a unit vector. We need a unit vector. So let's just call this r vector, and r vector has components x minus x naught and y minus y naught. Of course, we know what the magnitude of this vector is. It's not a unit vector, so we're going to take and normalize it to turn it into r hat, a unit vector. And that looks like this. I'm going to divide it by the magnitude of this vector, which requires Pythagoras' theorem. Right? The magnitude of this vector is the length of that, which is this. And now I've constructed the unit vector, and I need to bring this here, and overall, right, so in the denominator, notice that you have a term like this to the 1/2, because the square root means 1/2, and a term like that to the 1. And so overall, the expression for the electric field of a particle of charge q star that's located at x equals x naught, y equals y naught, has an electric field at xy that looks like this. Over something that has a power which is now 1 plus 1/2, which is 3/2. So it looks like that. Let's also notice that if we look at this triangle and we think of this angle and we call it theta, then we could write this in terms of theta, in terms of the angle, instead of in terms of x and y coordinates. So notice that this first component, which is x minus x naught, divided by this quantity, is related to this theta. So what is the cosine of theta? So the cosine of theta is equal to adjacent over hypotenuse. So that's x minus x naught over the hypotenuse, which is x minus x naught squared, plus y minus y naught squared to the 1/2. And the sine of theta is the opposite over the hypotenuse, but that's y minus y naught over the same thing. So I could actually write this in terms of cosine theta and sine of theta. And we'll stop there.